let's take a look at the limit as xy approaches maybe the point 2 pi over 4 of a function e to the x sine of y. So notice e to the x is a continuous function and sine of y is a continuous function. And the product of continuous functions is also continuous. And it means that this multivariable function is the product of two continuous single variable functions, and it's also continuous. And it means that to evaluate this limit, nothing's going to go wrong, and we can evaluate it simply by substitution. By that, I mean that I can plug in my values 2 for x and pi over 4 for y. Notice I'm also making use of the product rule. I could think of this as the limit as x approaches 2 of e to the x multiplied by the limit as y approaches pi over 4 of sine of y. Either way, by direct substitution, I see that the limit as x approaches 2 of e to the x is going to be e squared, and the limit as y approaches pi over 4 of sine of y is going to be the sine of pi over 4, which is square root 2 over 2. This is just direct substitution. Nothing surprising took place here. A more complicated example might be something like finding the limit as xy approaches 0, 0 for a function y squared x plus y divided by x, y. Again, this is the quotient of continuous functions. However, we see that the denominator function is equal to 0. So if I do try to evaluate this by direct substitution, so here I'll write this first attempt in green. My attempt, this is what I want to do, is just plug in 0, 0, and you end up seeing that that will give me 0 squared times 0 plus 0 all over 0 times 0, which is 0 over 0. So if I do direct substitution, I see that I get an undefined result. And the same rules of undefined results apply here as applied in single variable calculus. That just because I get a 0 over 0, this does not mean necessarily that the limit is equal to 0. The limit might not exist, or the limit might be 27, or some other random number. So we're going to have to do some algebraic manipulation before we can find this limit. So one of the things that I could look at, we see that this function isn't defined at the point 0, 0. That's what this just told us. But algebraically, this is equivalent to looking at the limit as xy approaches 0, 0 of the function. I'm going to factor a y out of the top and the bottom. Y times yx plus 1 divided by y times x. Here, I'm canceling y's. I recognize that at the point 0, 0, this isn't defined, but these limits will be equivalent. And now, look what happens. Oh, I didn't want to evaluate it at 0, 0. I wanted to evaluate it at 4, 0. Otherwise, this whole exercise is sort of pointless. Getting the y's to cancel, if I was approaching 0, 0, the limit still wouldn't exist, and it would have been a really boring example. But if I were approaching the point 4, 0, then look what happens. In this case, now I can do direct substitution. And when I do direct substitution, I see that I get 0 times 4 plus 1 all over 4, which is equal to 1/4. So we find that this limit does exist as xy approaches 4, 0 for this function, but it wouldn't exist at 0, 0. So that is a great lead into my final two examples. So for the final two examples, instead of showing what the limit is, we're going to show that a limit does not exist. So our first goal is to show that the limit as xy approaches 0, 0 of the function y squared divided by x squared plus y squared does not exist. So what does it mean for a limit to not exist? It means that as I approach this point 0, 0 along a number of different paths, those paths are going to be going in different places. So let's examine algebraically what it means for these to approach this along different paths. So for example, my first try, I'm going to approach this. We're going to approach the point 0, 0 along the path x equals 0. That means that I'm going to replace my x value with 0, because I'm moving along the path where x is always exactly equal to 0. Let's see what that does to my limit. That means that I'm now looking at the limit as 0y approaches 0, 0 of the function y squared plus all divided by 0 squared plus y squared. Maybe this is a weird thing to say, so I took my x's and I replaced them with zeros because I'm approaching along the path x equals 0. When I evaluate this, notice that I can evaluate this limit because I see that this is the same thing as the limit as y approaches 0 of y squared over y squared. And algebraically, by cancellation, we're able to see that this is exactly equal to the limit as y approaches 0 of 1. So in this case, as I approach 0, 0 along the path x equals 0, we see that our function values are going to be identically equal to 1 because my y squared divided by y squared cancel with one another, and I'm left with 1. But let's approach along a different path. So now I'm going to approach 0, 0 along the path y equals 0. So rather than heading at it with all of our x's exactly equal to 0, I'm now going to head at this point with all of my y's equal to 0. Algebraically, this is the limit as x comma 0 approaches 0, 0. And that's going to be setting my y's equal to 0, 0 squared divided by x squared plus 0 squared. Evaluating this limit, our y's are identically equal to 0. This is exactly the same thing as having my x's approach 0 of the function 0 over x squared. Notice that right when x is exactly equal to 0, this function is undefined. But the limit exists because every value leading up to 0 is going to have some positive denominator and a 0 numerator. And positive denominators with 0 numerators give me a limit of 0. So this is an example where we just proved that as I approach along the path x equals 0, my limit values were equal to 1, whereas when I approached along the path y equals 0, my limit values were equal to 0. I'm going in different places. This is our final and most tricky example. Now I want to look at the function xy divided by x squared plus y squared. And I want to show the limit as xy approaches 0 does not exist. So this is very similar to the previous example. I just shifted the function a little bit to give us one more technique. We'll do the same techniques as we did before, and I'll do them a little faster. If I approach the point 0, 0 along the path where x equals 0, notice what happens. We end up with the limit of 0y approaching 0, 0 of, with x equaling 0, our numerator is going to be 0 and our denominator is going to be y squared. And just like we saw before, that means that as we approach 0, 0 along the line x equals 0, we get a limit value of 0. As I do the same thing, only approaching 0, 0 along the line, along the line y equals 0, I'm looking at the limit as x comma 0 goes to 0, 0. Again, my numerator is going to be 0 because my y values are 0, and I get 0 over x squared, and that limit is also equal to 0 because I have a non-zero denominator for any value of x other than x being exactly equal to 0. So this is a good start, and it makes us think, aha, well, maybe this limit exists. I tried 2 different paths to get there, and both of those were exactly equal to 0 with their limit values. And this is where we're going to be a little clever. Now, instead of approaching along the path x equals 0 or y equals 0, I'm going to approach along the path y equals x. Look at what happens when I approach along the path y equals x. Algebraically, what's going to happen? Algebraically, I'm going to replace my y's with x's. So now x is approaching 0, 0. Graphically, in the xy plane, maybe I should do a 3-dimensional graph. Maybe that would be better. We don't really know what this curvy, crazy function is doing, but we knew it's doing something curvy and crazy. And I'm saying I'm going to approach the origin 0, 0 along this path, the path where y is exactly equal to x. It's the straight line through the origin. So when I evaluate it where my y is equal to x, I get x times x in the numerator, which is x squared in the numerator, divided by x squared plus y squared. But in this case, again, y I'm replacing with x. I get x plus x squared in the denominator. So what is this? So this is the limit as x comma x approaches 0, 0. And I can simplify this algebraically to get x squared divided by 2x squared. My x squareds can cancel, and we see this is exactly equal to just 1/2. So we found that as we approach along, I'll use a different color, as I approach along the line x equals 0, I'm getting the z value of 0. As we approach along y equals 0, I'm getting the z value of 0. But as I approach along the line y equals x, I'm going to be zooming in on z equals 1. So we have different limits along different paths, and it means that this doesn't exist. You might be asking me, well, how did I know to try this? How did I know that this was going to work? 1, practice. 2, we can use computers to be able to look at graphs of these functions, and that will give us a lot of insight into the types of paths that would be useful to evaluate to show that the limit doesn't actually exist. That's it for today.